Hi folks. So what I'm going to do in this video is finish up what we started on our last class, Wednesday, November 4th. The last thing we talked about was heat and question whether is this a different type of energy, and the answer was it depends on how you look at it. Macroscopically, we experience heat differently than we do our typical forms of mechanical energy, but microscopically it's just a change in the kinetic and potential energy of at the atomic level. So moving on from that, since we're on the atomic level, let's take a look at chemical energy. Okay, chemical energy. Heat given off in reactions, energy given off rapidly in an explosion, light given off by a candle. Chemical energy is the kinetic and potential energy of electrons in atoms. All right, so a quick review of the anatomy of an atom, a real basic model. The black circle in the center here is the nucleus, where our protons and neutrons are. We're not really going to deal with them too much. With chemical energy is dealing with the electrons, and the electrons are represented here as orbitals, as moving around this nucleus, and the red and green paths there represent where electrons would be. So electrons are in certain energy levels, if you remember from your chemistry, or quanta. There's certain states. They can't exist just anywhere. So a stable element, an atom of a stable element, is stable. It's in an equilibrium. It's okay the way it is, like this atom right here. But when two atoms are brought together, what can happen is this relative equilibrium. So let's put it that way, each individual atom has a relative equilibrium. Okay, doesn't have any better offers when it's by itself, so it's pretty okay as long as it's a stable atom, and which most of them are. It's okay. But when atoms are brought together, often, not always, but often, they can rearrange themselves into an even lower energy configuration, or more stable configuration. So when atoms are brought together, not always, but often, the electrons can often rearrange into a more stable configuration. Meaning a more stable equilibrium. Okay, so this interaction causes atoms to be bonded to one another. Okay, so you're familiar with chlorine, used to disinfect stuff, pools, cleaning, all kinds of stuff. It's pretty stable by itself, chlorine atoms. Sodium is a metal, highly reactive metal, but it exists in a pure form. When you put the two together, they rapidly join together, and they make table salt with much different properties than either the original components did. And it's a pretty stable compound, much more stable than the original ones. Sodium actually has to be kept in oil because it'll react with any moisture in the environment. Okay, so nuclear energy. Okay, up above, chemical energy was the energy of the electrons. Nuclear energy, same sort of thing, but now we're talking about the nucleus. So we're dealing with the potential energy and kinetic energy of the protons and neutrons. In the nucleus. So, for chemical and nuclear energy, we have a situation similar to heat. Macroscopically, we experience them differently, but microscopically, they're just changes in kinetic and potential energy of basic particles. Right? So, the thing is, it gets confusing for us learning this material in relatively modern times, because the equivalence of different forms of energy wasn't recognized till long after different fields of study were set up. So people were working independently of one another, thinking all these things were different. Each field comes up with its own units that were convenient for them, and all the units are equivalent, and they can all be converted to joules. But when you work in a particular field, you're going to deal with different units. And so a lot of your problems that you see in this class and other classes will use different units, because that's just the way it is. The fields are set up like that. And it's become convenient, become part of the ether, so to speak, in which those branches of physics do their thing. So, for example, the energy of subatomic particles. Is measured in electron volts. E, little e, big V is the symbol for that. So the equivalence for that, 1 electron volt is 1.6 times 10 to the minus 19th joules. Tiny little unit. When you consider a joule, isn't that big of a unit itself. But this is convenient because atoms typically have potential and kinetic energies around a few electron volts. All right, so it's a unit that's in the ballpark of those particles. and it's used in fields where equipment that deals with subatomic particles are, like when I did electron microscopy. The never used joules. You talked about the energy of electrons in keV, thousands of electron volts. Our microscope had was a 1,000 keV or 100 keV machine. So even though you could do it in joules, and that's a pretty big machine, you didn't. It's just part of the field. Electric power. That is the kilowatt hour. Kilowatt hour. 1 kilowatt hour equals about 3.6 times 10 to the 6th, 3 million joules. Okay, now this is on the order of typical appliances. All right, so typical household appliances like hair dryer, vacuum, use about 1 kilowatt hour in 1 hour. Right, so that's a convenient use for that field, or convenient unit. Thermal energy. There are many units used for thermal energy. The two most popular are the kilocalorie. The kilocalorie, which is symbolized by K, cal. These are, when you see calories in terms of food, these are kilocalories. A calorie is actually a pretty small unit. 1 kcal equals 4.187 times 10 to the third joules. So a kilocalorie is the amount of energy it takes to raise 1 liter of water 1 degree Celsius. Right, so that's how that's measured. British thermal units. BTU. British thermal units. You'll see this lots of places with insulation and furnaces and all kinds of practical everyday stuff. 1 BTU is 1.055 times 10 to the third joules. So a kilojoule, sort of roughly, if you're doing rough estimates. But something to take away from this is all forms of energy can be converted to one another. Okay, let's take an example we're full of every day, or experience every day. There is a fusion reaction that's going on in the sun. It's releasing energy, light energy that comes to Earth. That electromagnetic light radiation strikes photoreceptors in our eyes. It causes chemical changes in pigments, and that causes an electrical signal to go to our brain. And you could also take that light and recognize that green plants, store that light energy as starch. They use it to convert other materials, carbon dioxide and water, into starch to make up their bodies. So it keeps going round and round and round. All right, so so that wraps up section 8.3. The next videos, I'm going to have 2 more for you, and it's going to be sections 8.4 and 8.5, and that'll wrap up chapter 8. Okay, see you next time around.